Hello everyone. In previous class, we discussed about the various type of DC machines like permanent magnet DC machine and brushless DC machine. So in this lecture, study about what is armature winding, some important terms related to armature winding. Next, what is lap winding? What is wave winding? And after this, the difference between the lap and wave winding. And finally, the reference of this presentation. So in this presentation, we will cover all the topics. So let's start with armature winding. The armature winding is the most important part of the rotating machine. It is the place where energy conversion takes place. That is, the mechanical energy is converted into the electrical energy, and the electrical energy is converted into mechanical energy. So we can define the armature winding in a proper manner. The winding which carry load current is called as armature winding. So this is the definition of the armature winding. In this diagram, you can see the armature winding. Now we will discuss the winding of an actual armature. But before doing this, the meaning of following terms used in a connection with armature winding should be clearly kept in mind. So the topic 2, some important terms related to armature winding. So first one is pole pitch. It may be variously defined as the periphery of the armature divided by the number of poles of the generator, that is, the distance between two adjacent poles, is known as pole pitch. This is the simple definition for pole pitch. Another definition of pole pitch is it is equal to the number of armature conductors or armature slots per pole. For example, if there are 48 conductors and 4 poles, so the pole pitch is 48 by 4 is equal to 12. So by using this simple method, we can easily calculate the pole pitch. The second is conductor. The length of a wire lying in the magnetic field and in which an EMF is induced is called a conductor. For example, length AB or CD in figure 1. So this is a figure number 1. The third one is coil and winding element. The side of a coil means one turn or multi-turns is called a winding element. Obviously, the number of winding element is twice the number of coils. With reference to figure 1, the two conductors AB and CD along with their end connection constitute one coil of the armature winding. The coil may be single turn coil or multi-turn coil. A single-turn coil will have two conductors, but a multi-turn coil may have many conductors per coil side in figure number 2. So show the singleton coil, and figure 2 show the multi-turn coils. For example, each coil side has 3 conductors. The group of wire or conductor constituting a coil side of a multi-turns coil is brought with a tips as a unit and is placed in the armature slot. It may be noted that since the beginning and the end of each coil must be connected to a commutator bar, there are as many commutator bars as coil for both the lap and wave bindings. Number 4 is coil span or coil pitch, represented by Ys or denoted by Ys, is defined. It is the distance measured in terms of armature slot or armature conductor between two sides of a coil. It is, in fact, the periphery of the armature spanned by the two sides of the coil. If the coil span or coil pitch is equal to the pole pitch, then the winding is called the full pitch winding. It means that coil span is 180-degree electrical. In this case, the coil side lie under opposite poles. Hence, the EMF induced in them are additive. Therefore, maximum EMF is induced in the coil as a whole, it being the sum of the EMF induced in the two coil sides. For example, if there are 36 slots and 4 poles, then the coil span is 36 by 4 is equal to 9 slots. If the number of slots is 35, then the coil pitch Ys is equal to 35 by 4 is equal to 8, because it is customary to drop fractions. If the coil span is less than the pole pitch, then the winding is fractional pitched winding. In this case, there is a phase difference between the EMF in the two coil side of the coil. Has the total EMF round the coil, which is the vector sum of EMFs in the two coil side, is less in this case as compared to that in the first case, means full pitch winding. Number 5, pitch of a winding. It is denoted by capital Y. It may be defined as the distance round the armature between two successive conductors which are directly connected together, or it is the distance between the beginnings of two consecutive terms. So capital Y is equal to YB minus YF for lap binding, where YB is called the back connection or back pitch and YF is called the front connection or front pitch. And for the wave binding, Y is equal to YB plus YF. In practice, coil pitch as low as 1/18 of a pole pitch are employed without much serious reduction in the EMF. Fractional pitch windings are purposely used to effect substantial saving in the copper of the end connection and for improving commutation. Next one is back pitch, denoted by capital by B. Is defined the distance measured in terms of the armature conductors which a coil advance on the back of the armature is called the back pitch, and it is denoted by YB. As seen figure number 5, element 1 is connected on the back of the armature to element 8. Hence, the back pitch by B is equal to 8 minus 1 is equal to 7. Next is number 7, front pitch. It is denoted by F, is defined the number of armature conductors or elements spanned by a coil on the front or commutator end of the armature is called the front pitch, and it is designated by F. Again, we can use the figure 5. Element 8 is connected to element 3 on the front of the armature, the connection being made at the commutator segment. Hence, front pitch by F is equal to 8 minus 3 is equal to 5. Alternatively, the front pitch may be defined as the distance between the second conductor of one coil and the first conductor of the next coil, which are connected together at the front, that is, commutator end of the armature. Both front and back pitches for lap and wave windings are shown in a figure 6 and 7. So in a figure 6, we can see front pitch, back pitch, and resultant fixed pitch. It means by B is called the back pitch, by F is called the front pitch, and by R is called the resultant pitch. So figure 6 represented for lap binding and figure 7 represented to wave binding. Next one is resultant pitch. It is denoted by R. Is defined, it is the distance between the beginning of one coil and the beginning of next coil to which is connected. We can see figure 6 and figure 7. As a matter of precaution, it should be kept in mind that all these pitches, though normally stated in terms of armature conductor, are also sometimes given in terms of armature slot or commutator bar, because commutator is, after all, an image of the winding. So in figure number 6 and 7, we can see the by R. By R is called the resultant pitch. So next one is commutator pitch. It is denoted by C. Is defined, it is the distance between the segment to which the two ends of a coil are connected. This is the simple definition of commutator pitch. From figure 6 and 7, it is clear that for lap binding, YC means commutator pitch is the difference of YB and YF, whereas the wave winding, it is the sum of YB and YF, where YB is called the back pitch and YF is called the front pitch. Obviously, commutator pitch is equal to the number of bar between coil leads. In general, commutator pitch equal the plex of the lap bound armature. Hence, it is equal to 1, 2, 3, 4, etc. for simplex, duplex, triplex, and quadruplex, etc. So we will move on. The next important terms related to armature winding is single layer and double layer winding. So what is single layer winding? It is that winding in which one conductor or one coil side is placed in each armature slot. Such a winding is not much used. Double layer winding. In this type of winding, there are two conductors or coil side per slot arranged in two layers. Usually one side of every coil lie in the upper half of the one slot and the other sides lie in the lower half of the some other slots at the distance of approximately one pitch away. We can see in the figure 5. In this figure, the by B is equal to 7 and by F is equal to 5. In such winding, there are several set of completely closed and independent windings. If there is only one set of the closed winding, it is called simplex wave winding. If there are two such winding on the same armature, it is called duplex winding, and so on. The multiplicity affect a number of parallel paths in the armature. For a given number of armature slots and coils, as the multiplicity increase, the number of parallel paths in the armature increase, thereby increasing the current rating but decreasing the voltage rating. Now we will move on the next topic, name is lap binding. In a lap binding, the consecutive coils overlap each other. The first end of the winding is connected to the one segment of the commutator, and the starting end of the other coil is placed under the same magnets and joined with the same magnets of the commutator. This is the diagram for the lap binding. The conductors are connected in such a way that the number of parallel paths equal to the number of poles. Consider the machine has P poles and Z armature conductors. Then there will be P parallel paths, and each path will have Z by P conductor in series. The number of brushes is equivalent to the number of parallel paths. The half of the brush is positive and the remaining is negative. The lap binding is mainly classified into two types. They are the simplex lap binding and duplex lap binding. So simplex lap binding, in this binding the number of parallel paths is equal to the number of poles. Duplex lap binding, in duplex lap binding the number of parallel paths is twice of the number of poles. Next one is simplex lap binding. In lap binding, the finishing end of the one coil is connected to the commutator segments and to the starting end of the adjacent coil situated under the same pole, and so on, till and the coils have been connected. This type of winding derives its name from the fact it doubles or laps back with its succeeding coils. Following points regarding simplex lap binding should be carefully noted. Number 1. The back and front pitch are odds and of opposite sign, but they cannot be equal. They differ by 2 or some multiple thereof. Number 2. Both back pitch and front pitch should be nearly equal to a pole pitch. Number 3, the average pitch capital Y is equal to front pitch plus back pitch divided by 2. It is equal to pole pitch equal to Z by P. Number 4, commutator pitch YC is equal to plus minus 1. In general, commutator pitch YC is equal to plus minus M. Number 5, resultant pitch YR is even, being the arithmetical difference of two odd numbers, that is YR is equal to YB minus of YF. Number 6, the number of slots for a double layer winding is equal to the number of coils, that is half of the number of coil sides. The number of commutator segments is also the same. This is the diagram for simplex lap winding. In this diagram, we will calculate, firstly we calculate the back pitch by using the formula, and after this the front pitch. And if we have back pitch and front pitch data, so we can design the lap winding. However, where heavy currents are necessary, duplex or triplex lap windings are used. The duplex lap winding is obtained by placing two similar windings on the same armature and connecting the even numbered commutator bar to one winding and the odd numbered ones to the second windings. Similarly, in triplex lap winding, there would be three windings, each connected to 1/3 of the commutator bars. Number 7. The number of parallel paths in the armature is equal to M into P, where M is the multiplicity of the winding and P the number of poles. So taking the first condition, we have YB is equal to YF plus minus of 2. Number 8, if back pitch is greater than to front pitch, that is YB is equal to YF plus 2, then we get a progressive or right-handed winding. That is a winding which progress in the clockwise direction as seen from the commutator end. In this case, obviously, commutator pitch YC is equal to plus 1. Case number 2, if back pitch is less than to front pitch, that is YB is equal to YF minus of 2, then we get retrogressive or left-handed winding, that is one which advances in the anti-clockwise direction when seen from the commutator side. In this case, the YC is equal to minus 1. Actually, these data used in numerical. Hence, it is obvious that front pitch is equal to Z by P minus 1 and back pitch is equal to Z upon P plus 1 for progressive winding, and by F is equal to Z upon P plus 1 and by B is equal to Z upon P minus 1 for retrogressive winding. Obviously, Z upon P must be even to make the winding possible. The next topic is wave winding. The one end of the coil is connected to the starting end of the other coil, which has the same polarity as that of the first coil. The coils are connected in the wave shape and hence it is called the wave winding. The conductor of the wave winding are split into two parallel paths, and each path has Z by 2 conductor in series. The number of brushes is equal to 2, that is the number of parallel paths. So this is the diagram for the wave winding. As shown in figure 8, the conductor AB is connected to CD lying under S pole and then to EF under the next N pole. In this way, the winding progressive, passing successively under every N pole and S pole till it return to a conductor A dash B dash lying under the original poles. Because the winding progresses in the one direction around the armature in a series of waves, it is known as wave winding. If after passing once round the armature, the winding falls in a slot to the left of its starting point, then the winding is said to be retrogressive. If, however, it falls one slot to the right, then it is called progressive winding. Assuming a two-layer winding and supposing that conductor AB lies in the upper half of the slot, then going once round the armature, the winding end at A-B', which must be at the upper half of the slots, at the left or right, counting in terms of conductors. It means that AB and A-B' differ by two conductors. From the above, we can deduce the following relation. If P is equal to number of poles, then back pitch by B and front pitch by F nearly equal to the pole pitch. Then by A is equal to by B plus by F divided by 2 is equal to average pitch, and Z is equal to total number of the conductors or coil side. Then average pitch into P is equal to Z plus minus 2. So by A is equal to Z plus minus 2 divided by P. Since P is always even and Z is equal to P into by A plus minus 2, hence Z must always be even. Put in another way, it means that Z plus minus 2 divided by P must be an even integer. The plus sign will give a progressive winding and the negative sign a retrogressive winding. Some important point related to wave windings. Number 1, both pitches by B and by F are odd and of the same sign. Number 2, back and front pitches are nearly equal to the pole pitch and may be equal or differ by 2, in which case they are respectively one more or one less than the average pitch. Number 3, resultant pitch by R is equal to the sum of front pitch plus back pitch. The commutator pitch by C is equal to YA. In lap winding, YC is equal to plus minus 1. Also, YC is equal to number of commutator bar plus minus 1 divided by number of pair of poles. Number 5, the average pitch, which must be an integer, is given by YA is equal to Z plus minus 2 divided by P is equal to Z by 2 plus 1 divided by P by 2 is equal to number of commutator bar plus minus 1 divided by number of pair of poles. It is clear that for average pitch by A to be an integer, there is a restriction on the value of Z. With Z is equal to 32, this winding is impossible for 4-pole machine. Value of Z is equal to 30 or 34 would be perfectly alright. Number 6, the number of coils, that is NC, can be found from the relation NC is equal to P into by A plus minus 2 divided by 2. This relation has been found by rearranging the relation given in above. Number 7. It is obvious from 5 that for a wave bindings, the number of armature conductor with 2 either added or subtract must be a multiple of the number of poles of the generator. This restriction eliminates many even numbers which are unsuitable for this winding. Number next 8. The number of armature parallel path is equal to 2 into m, where m is the multiplicity of the winding. Now we will move to the next topic, difference between lap winding and wave winding. In a previous slides, we will discuss about the various important points regarding to design lap and wave binding. In our next topic, or topic number 5, we will study about the difference between lap and wave binding. So by using this table, we can differentiate lap and wave binding. First column, the basis of comparison. First one is a definition. So lap winding, the coil is lap back to the succeeding coil, and wave winding, the coil of the winding from the wave shape. Connection, the end of the armature coil is connected to an adjacent segment on the commutator. Wave winding, the end of the armature coil is connected to the commutator segment some distance apart. Next, basis is parallel path. In a lap winding, the number of parallel paths are equal to the total of number of poles. In wave winding, the number of parallel paths is equal to 2. Other name, lap winding also known as a parallel winding or multiple winding, and wave winding is also known as a 2-circuit or series winding. In a lap winding, EMF is less, and in a wave winding, EMF is more. Number of brushes in lap binding equal to the number of parallel path, and the number of brushes in wave binding is equal to 2. The types of lap binding is simplex and duplex, and the types of wave binding is progressive and retrogressive binding. The efficiency of the lap binding is less, but the efficiency of the wave binding is high. Additional coil in a lap binding, equalizer link, and wave binding dummy coil. Winding cost of the lap binding is high because more conductor is required, and wave binding cost is low. Uses: the lap winding used in low voltage high current machine, and the wave winding used for high voltage and low current machine. So this is the basic difference between the lap winding and wave winding. Next one is the reference of this presentation. So these are the reference. And thanks for watching the video.